Welcome from my side to this quite core framework-centric session. It even says so in the title now. This is very much about Spring Framework 5.2. Core container in the broadest sense of the term. We are going to talk about the messaging endpoint model and the, of course, the web stack as well in quite some form. But this is very much a representation of recent work that the team that I lead, the Spring Framework project team, worked on in just over the past like 12 months, right? So there's a lot in it and a lot that connects to other efforts around the Spring Framework 5.2 initiative. So like Spring Data, of course, the Spring Data Moore release train, and Spring Boot 2.2, which builds on all of this. But before we get in all that 5.2 specific, my narrative for this talk and the 3 sections I have for this talk are actually a little broader. So we're going to cover quite a bit of 5.2 specific stuff, but in the context of the themes that they connect to in the Spring Framework 5 generation. So there's also a bit of a general story around everything that happens in Spring Framework 5.0, 5.1, and of course 5.2, because those things really just connect to each other very, very closely. So there's quite a bit of stuff that we touch upon, but can't go all that deep in. I guess in this morning's keynote, I've made quite a lot of people check out the Kotlin and the RSocket sessions, which are really deep dives. We are going to touch upon Kotlin, touch upon RSocket here, but only in the context of the Spring Framework 5.2 effort. All right, so let's get into it. The beginning that I have for you here is about the initial section, is about the core API revision that we've started with 5.0. This is basically an ongoing effort. We take opportunity here of a baseline that we introduced in Spring Framework 5.0. We are finally able to take the entire API surface and the entire code base down to all of its internals onto Java 8+. Frankly, from an inside perspective, this is just one of the biggest steps we've ever taken. This revision that we've been doing here, and it connects to the next theme in just a moment, literally touched almost every source file. It is one of the deepest and broadest revisions to the core framework code base that we've ever done. So what does it actually allow us to do now? Well, previously, of course, if you remember, in Spring Framework 4.3, there was a Java 8 support story, but it was all based on a Java 6-based kernel, a Java 6-based core container with optional Java 8 support. In typical Spring style, it automatically kicked in if you were running on Java 8 or higher, right? So if you were using Spring Framework 4.3, it might already have felt like a Java 8 oriented framework to you, but it actually wasn't Java 8 based. It was adapting to Java 8 API types, to Java 8 language use in your code, but internally in our code base, we couldn't make use of any Java 8 constructs. We just had optional Java 8 support everywhere. All right, so this is essentially what we are doing here, what we have been doing in 5.0 as an initial revision, and what we keep elaborating on in 5.1 and 5.2. Just a little bit of insight into what Java 8 enables here. It's not only the Java 8 language constructs. For framework providers, as we are, it's even more important that we have the core library level in Java 8 available to us. Stuff like the Java util function interfaces, completable future, the java.time types, instant duration, and so forth. Collection streams, the stream API, that we have these facilities available, that we're able to expose them from APIs of our own to your code for more sophisticated interaction according to Java 8 API conventions with Spring APIs that you're calling. This is really a very, very, very important enabler. More important than our internal use of Lambda expressions and method references for sure. The other part that I find particularly important is the default method arrangements in interfaces. As of Java 8, we can declare, you can declare, of course, we can declare Java 8 or Java interfaces with default methods. So there's a bit of a breakage with a good old Java tradition. Interfaces are generally consist of abstract methods, of course, but now we can add default methods, introduce new methods to existing interfaces that are declared as a default method, so with basically a default implementation that usually delegates to other methods within the same interface. That is one thing. That is actually that is what Java 8 default methods have been introduced for in the JDK, allowing for interface evolution, introducing new methods without breaking existing implementations. But that is only one part. I find the other part almost more important for us. We are also empowered to redeclare existing methods in existing interfaces that had to be abstract, of course, pre-Java 8. And we are now able to redeclare them with default bodies, as default methods with a method body. For convenience, right? Existing implementations keep working, of course. They implement all the methods. But as of Spring Framework 5, if you're implementing, say, the handler interceptor or beam postprocessor or those kinds of interfaces with several callback methods, most of them are now declared as default methods. And you only implement the one you're really interested in. There's no need for adapter classes for stubs anymore. So this is actually this is something we've been doing to a lot of the existing surface. We've been revisiting it. And we've also been revisiting all the interfaces. And quite a few of them have been redeclared with default methods if that makes sense for that interface's purpose. All right, let's get back into our themes, the refactoring efforts or the redeclaration efforts that we went through here. We've been going through for a number of years now. The other one, next to the Java 8 baseline, is nullability, a slightly more unusual one or unexpected one, I guess. We didn't really have much of an upfront plan before Spring Framework 5. This kind of evolved during the Spring Framework 5 preparations, where we encountered a need for hard, strict declarations of nullability, of nullable arguments, of nullable return values, all over our API surface initially. Of course, Java traditions bring it with them that nullability is usually just somewhere in the Java docs, right? There's no standard Java language feature allowing to declare nullability. So we historically weren't really able to do anything about that part. But then along comes Kotlin. And Kotlin, in its language, has a clean and strict nullability arrangement where you might call some method and assign the return value from that method to a non-null variable declaration within your Kotlin code. Now, Kotlin only allows for doing this, allows you to do this, if the call that you're making has a clean nullability declaration for its return value. This is the case for many Kotlin APIs. It's basically not the case for common Java APIs. There is a layer on top of the core Java libraries that they're applying for nullability semantics on top of those. But if you're calling third-party APIs like the Spring APIs, it basically defensively has to make an assumption that this could potentially be null. And this is, of course, a Kotlin integration problem as it materialized for us, but it really revealed itself as a more common problem. Where even for a Java method call, you find yourself calling target APIs all the time, and if you're not entirely sure whether this could ever be null, you have to apply a non-null check to the return value that you got even in Java. So long story short, we started introducing nullability annotations. We started embracing an approach that quite a few other libraries and tools have already been using at nullable and at non-null declarations all across the code base. So instead of putting it into Javadoc, putting it into an annotation is already quite a formal step, a step that tools can reason about, and a step that we can also validate. So for a start, we found out that IntelliJ IDEAS support is actually really great. IntelliJ IDEAS constant conditions and exceptions inspection is great for validating your assumptions against code that you're calling. So making sure that you're not missing a potential null value, running into a null pointer exception. Also the other way around. not being overly defensive. If your code path is always non-null, IntelliJ IDEA or other similar tools can validate this for you and basically point out that you have an unnecessary non-null check there. Both of those effects, of course, when we applied this to the core framework code base, both of those effects showed in many places, right? So we went through the entire code base from the very surface area down to the inner workings, down to all the field declarations, and applied nullability annotations to them and ran in particular the IntelliJ tooling against it in order to clean up the code base in all directions. There weren't that many places that really turned out to be a real bug. It's more of a form of refactoring, an improvement to the code base, a straightforward revision of the code base that went nicely along with our Java 8 baseline revision. So the end result is that we are now shipping a code base that is fully declared with nullability annotations. Make use of this in your code. If you are calling Spring APIs, double check what the API reference says. Go into the Javadoc declaration, which also has the nullability annotations. Maybe use IntelliJ's tooling or the corresponding Eclipse tooling to validate the assumptions that your code is making against calling Spring APIs now. The use of nullability annotations is empowering you to do this. And it's not just us doing this, it's also, for example, RxJava, OK HTTP. There are other libraries out there that have the same kind of nullability annotation story. And of course, for Kotlin users, this is now really enabling a very natural use, a very idiomatic use of Kotlin, right? You can finally call all the Spring APIs with a strict nullability assumption and assign them to Kotlin variables as you would with a native Kotlin API. All right. A couple of other things before we dive into the performance topic in particular. A couple of other hand-picked selections, favorites of mine in 5.1 and 5.2. There's a revision of the ObjectProvider facility, also motivated by Java 8 and nullability. And just to give you an indication of what we're doing here, ObjectProvider is not old, but older, like dates back to the 2.4.3, to the 4.3 line. ObjectProvider is an older API that we revisited. So it had some existing methods, like getObject, of course. It's basically, what is ObjectProvider? It's an indirect handle to a target object, right? If you inject a at AutoWired foo instance into your code, you could also declare it as ObjectProvider of foo, which is sort of a lazy indirect handle to the actual foo instance. You would call getObject on it. You would only do this when you actually need the foo instance. You can also interact with the container, ask it if that instance is even available, whether there's a unique instance that can be resolved. There might be several foo instances managed by the container after all. So it comes with methods like getObject, getIfAvailable, getIfUnique. Now, we redeclared those existing methods with nullability in place here, as shown here in the middle section. Because semantically, getIfAvailable and getIfUnique are great examples for nullability issues, right? They are declared as, give me the object if it's there in the container, if there is an object available, if there is a single unique object, give it to me, otherwise return null. That's how those methods have been operating and how they have been declared in their Javadoc. As of Spring Framework 5, those are now annotated with @nullable, giving a clear formal indication that their return value can be null. Now, that's not where we stopped our efforts. A good indication for what we've been doing recently and what we keep doing here are the methods below. We introduced new methods now to the existing interface with a slightly different arrangement, right? A slightly more functional arrangement. The Java 8 as a kind of generation of the API that comes with Java also introduced a sort of functional style, collection streams, the Java util function interfaces. And along those same lines, we have new methods like getIfAvailable with an argument, a Java util function supplier, a default supplier that is supposed to produce a default instance if the container doesn't have a managed instance that matches the type T. Now, of course, such a method will never return null. It will return the container managed instance or the one produced by the passed in default supplier, which is usually a lambda expression or a method reference. It will never return null. We have a default convention and non-null API conventions for all our packages. So if there's no annotation here, no nullable annotation, it will never be null, non-null by default. So those methods never return null. Get if available and get if unique. Follow that design guideline. There's two other flavors, even slightly more functional, right? If available and if unique. So you could also say, if available, here's a Java util function consumer. You get a callback to the code, to the lambda expression usually that you're providing, only if the instance is actually available in the container. And otherwise, we just skip that step and it's a no-op. That is actually, in terms of a functional API flow, the nicest variant. Right, so a good example for how we integrate the Java util function interfaces and this kind of collection stream design style into our API world, into our API surface here. We go a little bit further than that. So these are existing methods, of course, again, but let's focus on a different part here. And these date back to 5.1 last year. We also allow ObjectProvider to interact with several matching instances in a first-class way. You could iterate over all matching instances in the container with a good old iterator. But you can also use a Java util collection string, right? A Java util stream as provided by collections as well. So there's a stream method, like on a Java util collection now, and an ordered stream method with strong ordering semantics, sacrificing a little bit of lazy initialization semantics over ordering semantics. That's why there are two streams. But these methods, of course, allow you to do a collection-style interaction. Take an object provider, say object provider stream, filter according to certain conditions, and do for each interactions with every matching instance in the container. So that's part of the motivation to apply Java 8 API style and semantics to our APIs. Are these kinds of interactions. They really sit nicely next to Java 8-based code for collections, for example. All right, before we move on to good old Spring Framework 5.0 examples, keep in mind that not only can you programmatically interact with the container along these lines here, where you basically get a reference, a programmatic reference, and query the container, interact with the container through programmatic facilities. And these are pretty wide-reaching. You can get these provider through annotation-based injection, or you can get it through a programmatic call, right? Then it's the same code from there onwards. This is one side of the fence. The other side is, of course, registration. And we already covered most of this in 5.0, where you can take a generic application context and provide all of its configuration, all the beans that you intend to register through programmatic calls. And they follow, of course, a similar style. Those register bean methods, dating back to 5.0, are kind of the other side of that coin. Programmatically registering a bean of type foo or a bean of type bar with default instantiation through the constructor, or with an instance provider, as we're calling it, an instance supplier, as we're calling it, where a passed-in lambda expression adapted to a Java util function supplier is now going to build the instance whenever the container needs it. So this is also a callback style arrangement. Instead of doing a configuration class with add-bean methods that have to be reflectively called, you register a definition with an instance supplier instead. The instance supplier, basically this thing here, is the equivalent of the add-bean method, but expressed as a Java 8 lambda expression. The container is still in charge of the lifecycle. When this is a prototype or a request scope bean, it would call this supplier whenever a new instance is actually needed. And there's a bit of fanciness there in what you can express. So if bar does not accept a foo instance, but rather an object provider of foo, you can call back to the container to get this object provider, as shown before. And there's the bean definition customizer facility illustrated below here, where you can pass an additional lambda expression, or even several additional lambda expressions in, and they get a chance to modify the bean definition before it is registered with the container. This is kind of an underlying metadata object that has everything on it. You can set lazy init here, you can add qualifiers, you can add bean definition attributes, whatever you need, whatever your post processors need, whatever the rest of your code needs, right? So there's full access to the underlying container facilities. And in a pure scenario, you could configure an entire application along those lines. In practice, it's of course more of a mixing and matching scenario. You can always go out and scan for bean definitions, add them to the same context. You can read XML bean definition files, add them to the same context. So there's a mixing and matching where certain beans can come from a class path scan, others can be programmatically registered. As usually in Spring, as you probably expect Spring to go about this, mixing and matching many shades of gray in between. But also a pure fashion if you wanted to, right? A pure fashion without any class path scanning, without any reflection, without any annotation retrieval is basically what you're getting with this approach shown here. And you choose to add further facilities like annotation support, like class path scanning as you need it, as you want it. All right, and for a little bit of Kotlin, this is the basic Kotlin extension arrangement we have for generic application context. There's a little bit more. Kotlin also allows for DSL style bean definitions here, but this is the immediate translation of what we've been seeing here. And to give you an idea of how this actually works, this looks equivalent, but it's not actually calling the same methods. It's calling methods declared on an extension, a Kotlin extension, to the generic application context class. So you're using the actual same Spring context jar, the same generic application context type, but through your use of the Kotlin compiler, the Kotlin compiler automatically discovers that Spring ships extensions for this particular type. So whenever you're using Kotlin, you see further methods on that type that are not there when you're using the basic Java type. A Kotlin language facility, a Kotlin compiler facility that we're making good use of here. So these are actually overloaded register bean methods. This one takes a K class, this one takes a K function, so the equivalent of a Java util function supplier, but with certain benefits that come with it. You don't need to say foo class.java, as sometimes you have to do when adapting Kotlin code to Java code. And here, you don't actually have to repeat the bar type. A Java util function supplier, a lambda expression here, does not reveal which type it is actually returning. So there's no way for the framework, no proper way for the framework to infer the return type. That's why we have an explicit argument where you're saying bar.class is my component type and this is how I'm going to instantiate it. There's no need for that extra argument in Kotlin because a Kotlin K function has a well-declared compiler-provided return type that we are inferring here through Kotlin reflection APIs. And this is just a bit of a fancy rearrangement where we're making some use of Kotlin language styles to call the same methods with the inline generics in Kotlin. Has a bit of a DSL feeling to it and looks to me always a bit similar to the Gradle's Kotlin DSL, the Gradle build tool and the Kotlin DSL it's providing. All right, so much for a bit of lower level insight into the work that we've been going through there. And let's move on to the next section, performance tuning. The performance tuning part of it is, of course, that's a never-ending story, right? Is software ever fully performance tuned? You're never at the end of any line here. But we keep investing into this. And there are quite a few new facilities in recent Spring versions and in 5.2 in particular that allow you to fine-tune the performance impact of what you're doing, of the components that you want the container to manage. So for a start, a rather obvious one, maybe too obvious, where it's often overstated in terms of its impact, is component scanning. Obviously, a component scan is somewhat costly. It goes through the class path, finds all the base packages in the jars and the class path directories of your setup, and it's introspecting all the class files in there and trying to find matching types that have like an add component, add service, add controller stereotype on top by default. This is, of course, somewhat costly. You can replace this anytime in any Spring-based arrangement with explicit enumeration of the classes, right? Instead of saying scan this base package, you can always say register these classes and enumerate them. And in particular, in microservice architectures, this is totally feasible because in a corresponding scale of application context that you're building, there might be a really, truly enumerable number of components in there. Well, there's another variant that we're providing and that has been spiced up for 5.1, even if it dates back to 5.0. That's the Spring Context Indexer. It's a build-time annotation processor that spits out a Spring.components file to be included in your jar files, in the application jar files. They basically pre-index the classes that are annotated with Spring stereotypes. So by using this annotation processor, by including it in your build, you can bypass the actual component scan. A little bit of class introspection is still going on, but only for the classes, for the narrowed set of classes provided by these Spring components declarations. That being said, most of the time, this is not where startup performance really suffers. Component scanning in a setup without a JVM security manager is actually pretty fast. So only go to that length if you have already found out that component scanning is actually the culprit in your startup scenario. And if you're actually trying to optimize for startup performance, of course, to begin with. A huge topic in 5.2 is the annotation processing effort that Spring has to go through. We've had that, of course, for a long time. Facilities for annotation introspection, for meta-annotation introspection, where Spring's composable annotations, where you build your own annotation and they are meta-annotated with standard ones. All of this, of course, takes some effort to kind of reason about, to find out about on startup. The facilities that Spring has had for the longest time, annotation utils and annotated element utils, are still there, but they are now backed by a complete re-implementation of the annotation introspection facilities with more centralized points to go through. So basically, it all goes down to very few points of retrieval. It's not spread out anymore. We are enabling improvements to the annotation lookup mechanism at runtime. This is not currently publicly exposed, so we only have internal prototypes to prove that this actually works, right? That we can replace the source of annotation metadata, centrally replace it with other sources like pre-generated annotation indexes. At this point, we have not really had convincing benchmark results with those, right? An annotation index that is basically a binary file somewhere in the class path also needs to be read and to be parsed on startup. That is costly in its own right. And in the scenarios that we tested, it is most of the time as costly as the annotation introspection through reflection is. So we haven't really made it a first-class feature in this generation. We might make it a first-class extension hook in 5.3 if we find arrangements, if we get benchmark results, also from any stakeholders, of course, that prove that that certain arrangements, certain SPI facilities allow to efficiently integrate with a particular index arrangement that provides better startup performance for an application overall, since that is the goal, what we're working towards here. The Merged Annotations API, as sort of a side effect, is also a more sophisticated little functional style with a builder API. It is a new, better structured annotation retrieval API for Spring's common annotation purposes. So taking into account the annotation composability, the meta-annotation models, it's a nice new central entry point, API entry point for sophisticated annotation introspection in Spring. So at least that part is already providing benefits to certain callers in 5.2. If you can efficiently express your annotation retrieval needs as for example, in a third-party extension to Spring, you can now do so with merged annotations, allowing for some runtime improvements right away, simply through expressing your retrieval needs more expressively and allowing for some optimizations underneath the covers through that. We, of course, spent, I don't know how many iterations, improving standard reflection performance, standard annotation introspection performance. I'm not explicitly mentioning this on the slides, but simply by upgrading to 5.2 and making use of the re-implementation underneath the covers without any changes to your application or to your configuration, you are going to see better performance, better startup performance for sure, better annotation retrieval performance, even at runtime later on. So even if you're not doing anything fancy about it, just upgrading to 5.2 is already worth it on its own. And to boot to the 2, of course, many of those aspects reveal itself, in particularly in boot applications. Now, that being said, for some optimizations, we need your cooperation. There's many things we can do transparently through refactoring, through optimizations, through caches underneath the covers. But there's limits to what we can do there. Some component model constructs that we have in the Spring component model are just kind of costly by design, right? A configuration class is somewhat involved in how we need to handle it. You want to call an add-bean method from another add-bean method, and you expect a container to intercept the call. Well, that means we need to create a runtime subclass for it, a glib subclass for it. That is somewhat costly, not for a single configuration class, but for many configuration classes, it is going to show in terms of a bit of your startup performance. By opting out of this through saying add configuration proxy bean methods equals false in 5.2, you can basically say I'm never going to do these inter add bean method calls in this particular configuration class anyway. So skip basically all, and no other configuration class is going to call the add bean methods on this configuration class either with that semantic assumption. If that is the case, you may add that little flag, opt out of that mechanism, and skip glib subclass generation for this particular class. This is, of course, for configuration classes. glib is also being used in the AOP framework a lot. Generally speaking, interface-based proxies are easier, more efficient to generate on startup through the underlying Java Lang Reflect proxy facility in the JDK. glib proxies for AOP purposes are also somewhat costly. So if that is an issue, if startup performance is an issue, consider using interface-based proxies instead. And there are other reasons to do this, of course, depending on which JVM setup you're running on. glib might not work at all, and interface-based proxies might work out of the box, so there might be side benefits to it. Last but not least, or actually first on this slide, keep in mind that for certain target scenarios, maybe microservice scenarios where there are hotspots, where certain services suffer from very specific characteristics in an annotation-based setup, you could always replace it and re-implement it with a pure programmatic setup along the lines of those register bean methods shown before. Build a Spring application context, register exactly what you need and not more. Everything through the programmatic facilities, no component scanning, no reflection on factoring methods or anything else. No annotation processors even registered at runtime. So no piece of Spring even tries to find an annotation. If you know that there are no annotations in your setup anyway, start with generic application context and not annotation config application context, and you save quite a lot of CPU cycles simply by not ever trying to look for an annotation that will never be there. This is by far the most efficient way to bootstrap a Spring-based service setup. Of course, it might or might not matter in your particular scenario. Maybe it only matters to very specific services that you could consider refactoring towards such an arrangement. For milder touches in existing Spring applications, those facilities are maybe more interesting. Now, that being said again, there's only so much that we can do at the core framework level or at the Spring level in general. The interaction with third-party libraries is often the source of a lot of overhead, or a lot of the startup cost in particular is actually in bootstrapping third-party providers or even external services, external connectors. A particularly well-known suspect is the persistence provider, Hibernate in particular, where in a typical Spring-based application, easily half or more of your startup time is eaten up by Hibernate alone. So if you shave a few milliseconds off the Spring startup, it's not really going to show if Hibernate keeps eating more than half of your startup time. Of course, Hibernate is moving along those same lines. And the very recent Hibernate ORM 5.4.5 release, just a couple of weeks old, also comes with a couple of performance improvements again and a couple of configuration options. Hibernate is highly configurable, and there's many ways to go about improving its own startup performance. It's never going to be really quick to bootstrap, but you can get way beyond a standard Hibernate startup experience through fine-tuning it. And there's many ways. There's the Gendex index integration. There's the different bytecode enhancements mechanisms that it has. There's also different tunings for its memory consumption, because that's the other part. The persistence provider really eats a lot of memory. Right, so much for Hibernate. Another typical optimization, a third-party library with optimization demand is Jackson, or generally speaking, any kind of JSON conversion libraries. This is particularly important at runtime, not necessarily just for startup purposes, where depending on the setup, you might see significant gains, at least also in response times, in response generation times or request parsing times, through fine-tuning the Jackson setup. Of course, JSON on its own is somewhat expensive to parse. You might want to consider some of the alternative data formats that Jackson supports that are just more efficient to parse. That's the main reason for those alternative data formats is simply performance. It's parsing performance for those. That's the reason why they exist. Otherwise, you could always use JSON anyway. Right, so that's also something we focus on our end. We keep track of everything Jackson does, and we support the brand new Jackson 2.10 release now. Remember, we have a new baseline. As of Spring Framework 5.2, we only work with Jackson 2.9.7 and higher for some API interaction purposes. All right, so don't forget the third-party libraries. They can be a huge part of your performance profile, both for startup and for request processing performance in a web architecture. Now, two forward-looking stories along that line. We have been experimenting with GraalVM Native Images for the longest time now, so for more than a year. Right? We've been pretty early with prototyping the use of Substrate VM, of this kind of native image tool in GraalVM, to find out what it takes for a Spring-based application to be turned into a Graal native image. Well, basically, this tool is going to take an existing Java-based setup, a Java-based application, going to turn it into a native binary. This is somewhat costly. The native image tool, literally, it takes minutes, even for a simple application. So this is not something that you quickly sneak into your build. But the outcome of it is, of course, a native binary that bootstraps almost immediately. There's no JVM warm-up cost. There's very different memory usage in a native image. So a motivation to use it is not only startup time, but also the reduced memory consumption. Garbage collection works in a totally different way, with less memory being consumed up front. So it's quite a different setup. There's a few things we have been sneaking into earlier Spring Framework releases in order to be kind of forward compatible with Graal constraints, because keep in mind, there's a lot of constraints here. This is a totally non-trivial topic where there are just many things that do not work in a native image out of the box, or not at all. Some things do not work at all. Others only work with certain configuration being provided to the native image tool up front. And this is exactly where we find ourselves here. We have been doing everything we can in 5.1 and 5.2 to kind of not be in the way of native image constraints. But in order to take a real-life Spring-based application and turn it into a native image, it's still currently up to you to provide the corresponding Graal native configuration, which usually means you need to basically list all the classes that are being reflected upon, because whatever you might have read about GraalVM, it actually supports many things. It does support reflection. It just needs to know upfront which classes are being reflected on. So providing them in a little configuration file, providing them to the native image tool is all you need to do. But it's currently manual. You need to manually craft that file. The same goes for proxies, proxy classes. You need to basically provide them upfront. The native image tool is going to pre-generate the proxy classes needed later on at runtime, and it's going to include them in the native image. This is all doable, but requires explicit configuration at this point. We have a summary of the current state of the art of our understanding what it takes to get there on our wiki. We are working towards a nicer out-of-the-box experience. That doesn't mean that you can just switch a flag and use a native image. It's never going to be like that. There are always going to be constraints applying. You're always going to architect for deployment as a native image. You have to take this into account in some way at least, even within the application, within your code, within your components. But from a Spring perspective, providing, for example, a build time step, a build time processor that takes typical Spring convention, infers classes that are being reflected upon, and generates the corresponding Graal configuration up front, right before you call the Graal native image tool. This is what we're working towards. A smoother experience where you don't have to repeat yourself, and where standard configuration for Graal for the native image tool can be inferred from Spring conventions in a standard Spring application. This is what we intend to provide in the 5.3 timeframe. We'll see where it goes. There are many little issues still in the Graal native mode in general. The GraalVM team at Oracle is very open-minded, also very willing to collaborate with us. There's already quite a long line of collaboration here, and this is only going to intensify from here towards the GraalVM 20 release mid-next year. So we'll see where this goes. This will take some consideration on the GraalVM side. It will take quite some consideration on our side, in particular in extra pieces like build time steps that we provide, and a little bit of guidance. It's mostly about guidance, about corresponding documentation for how to turn a Spring application into a native image and for what to take into account, so that you don't have to individually find out yourself every single time, so that we pre-compile the state-of-the-art understanding into a wiki page or a documentation setup. All right, so much for GraalVM. Another even more forward-looking note is Project Loom. Project Loom is in all applicable brevity, probably the most interesting, most exciting OpenJDK project there is that has a chance of making it into the OpenJDK mainline somewhat soon. It is essentially a fiber model, a sort of lightweight thread variant where we're not using operating system threads as we do now for all purposes, but where we have a new notion of a lightweight user mode thread, of a fiber, that can be very efficiently scheduled within the JVM itself. There is already a prototype for this, like OpenJDK with Loom early access builds. The way it currently works is that the thread semantics transparently apply to fibers. So if you're running a JVM in fiber mode, then stuff like thread locals, thread.currentThread, they implicitly return the current fiber local perspective, right? So then fibers are basically a variant of a thread in that world. So what's the benefit of fibers? Well, it's in particular scaling. You can have thousands, tens of thousands of fibers easily within any JVM, where the same JVM setup would otherwise be bound to 150 or 200 threads for real-life purposes. So you can take a simple setup, the same resources as before, take a fiber-enabled JVM, and get a much higher degree of scalability. Scalability with code that tends to be blocking, right? Like a servlet container, like Tomcat, where every request that comes in and waits for some data to arrive before it returns, before it generates a response, is going to block and wait for the data store, block and wait until the response can be written out. So traditional servlet API semantics, Spring MVC on Tomcat is a fine example for this, where the introduction of fibers will really bring a dramatic difference in scalability to such existing servlet API-based architectures. And that's kind of a very interesting impact for us as well. We have to see how it actually materializes in the OpenJDK mainline. It has a chance of making it for the JDK 17 long-term support release in 2 years. So it might be somewhat close already. And it might bring a new category of scalability to existing Spring MVC applications. Maybe there's less need to architect in a different way then. Maybe it's more feasible to keep using servlet-based architectures for a larger class of applications out there. We'll see. Our duality of Spring MVC on the servlet stack and Spring WebFlux on a reactive architecture, native-based or event loop-based kernel underneath the covers is going to remain with us for the foreseeable future in any case. Even a reactive architecture can benefit from fibers, but the more dramatic impact is certainly going to be on the servlet stack, and we'll see maybe this provides a bit of a shift in terms of what the Spring MVC is being used for versus Spring WebFlux. At the same time, of course, Spring WebFlux has unique characteristics with the reactive streams-based architecture underneath the covers that go far beyond what fibers are going to provide here. Fibers are essentially just a more efficient and more scalable form of a traditional blocking I/O interaction architecture. And a reactive streams-based architecture with full back pressure support is, in a stream-based architecture to begin with, is just in a different kind of architecture. We'll see where this goes and how it impacts architectural decisions going forward. It's something that's very immediately on our radar, and we'll try to make the best of it for both worlds, for the servlet stack and also for the reactive stack. Talking about reactive, my final section that I have for you today in this somewhat deeper dive into core container characteristics is a fresh perspective onto our use of reactive facilities and reactive programming model elements, in particular at core framework level. There's plenty. There's some parts of this are new or revised in 5.2. I just want to summarize and kind of re-summarize what you actually can do and how flexible you are in choosing to use reactive facilities in Spring these days. So let's start with the most common elements. That's, of course, the use of reactive web endpoints. That's mostly, of course, connected to Spring WebFlux, where you're building a controller class, and the controller has several endpoint methods with the usual mapping annotations on them. But the methods themselves are designed for a reactive streams architecture. They are reactive endpoints. They don't actually process any part of the request. They return a reactive pipeline with instructions for how to process the request as we are in a situation to actually do it at runtime, right? So it's basically building a reactive pipeline of instructions, of steps to take to get from the request to the response. The typical indication is the return value. If this is a reactive type, as we call it, typically a reactive streams publisher implementation, like a reactor mono or a reactor flux, then we know that this is a reactive method. And we're going to take it as what it is, right? We're going to take this reactive streams publisher and going to connect it to our request and response processing chain. And we're going to, when the request is ready to be read, we're going to start processing it through subscribing to this pipeline, through dispatching elements through to the subscription behind this arrangement. Now, this reactive type support is, of course, a feature of WebFlux, of the WebFlux stack. If you choose to run a set of reactive endpoints on a, say, Netty and Reactor Netty and event loop stack for your web architecture, then you're bound to designing all your endpoints along those lines. So everything you deploy onto Spring WebFlux has to be reactively enabled. It has to be a reactive endpoint. There's no way you could mix and match here. WebFlux is a pure stack. An event loop-based architecture, you must not ever do blocking operations, blocking endpoints, blocking API calls here. So it's kind of the pure version of it. At the same time, you can also deploy such endpoints or design such endpoints, reactive endpoints, as part of a Spring MVC architecture. So what happens if you do this to Spring MVC? If you set up a Spring Dispatcher servlet and provide it with a controller that returns a Reactor Mono or a Reactor Flux. Well, we do the best we can. We understand these are reactive types, even within Spring MVC. We're going to switch the servlet request into the servlet container's async request mode, and we're going to adapt the returned Reactive Streams publisher to the async I/O model that the servlet container provides. It's quite a different mode of execution in the servlet container, but it's a standard servlet 3.1 and higher feature. So that's what we adapt to. It's not quite as efficiently processed as it would be on an event loop, on a netty-based architecture, but it's the best we can do on a servlet container, and it might perfectly be good enough for your purposes. The sweet spot on Spring MVC on the servlet stack is you can mix and match standard endpoints, the ones that build views, that render templates, that call JPA, whatever, and mix and match them with a few reactive endpoints. Maybe for some server-sent event endpoints, maybe for some longer running download endpoints, whatever it is. You can choose to selectively use reactive programming and reactive streams publisher return types even within Spring MVC on any servlet container, on any recent servlet container. All right, so this is the way we see reactive facilities in the Spring programming model. They are not exclusively applied to just a particular version of the stack. Wherever possible, reactive programming elements are going to be usable even in a differently composed Spring architecture, anywhere you choose to use it, right? Even on Spring MVC. New in 5.2 is reactive transaction support, kind of along the same lines. We have edge transactional methods. We discover, just like we do for a reactive web endpoint, looking at the return type, we know it's a reactive type, it's a mono, it's a flux, it's a reactive streams publisher. So imagine the framework comes along, sees a method like this. Does it make sense to intercept the beginning of that method, do a thread-bound transaction, call that method, return and commit, as we usually do for an edge transactional method? It doesn't, right? This method is basically a factory for a reactive streams publisher. A thread-bound transaction doesn't make any sense here. As of 5.2, what we're doing is, if we discover a reactive type return from a transactional method, at the transactional boundary, we switch into a different mode of transaction management, reactive transaction management. We're looking for a reactive transaction manager implementation in your context. There needs to be a specific transaction manager chosen, a specific setup chosen. And this reactive transaction manager is then going to work in a completely different fashion. It does apply transactional boundary semantics, but it does so essentially through decorating the reactive streams publisher. It takes this mono or this flux, sneaks a transaction context into the reactor context within that pipeline. So any downstream call, like the repository dispatch to here, may then see a transaction context and may interact with that transaction context. It needs corresponding data access code underneath the covers that is willing and able to participate in such a transaction. And then when the pipeline basically finishes its execution, at the very end, we're going to complete the transaction. So it essentially does the same thing that a thread-bound transaction does, but it applies it in a different way. We can do this to essentially any reactive type, but it's most straightforward if you use the reactor types, as we commonly recommend. If you use mono and flux, there are dedicated code paths for optimizing it when you choose to use those. Now, what would you use it with, right? What kind of target data store? Well, you need a reactive transaction manager implementation, and you'll find them currently in the Spring Data project. Spring Data Neo4j, Spring Data MongoDB, and Spring Data R2DBC come with reactive transaction manager implementations in the Spring Data Moore release train. So all of them are designed to work with this model. But you do need a corresponding driver that actually supports this. All right, and R2DBC, of course, is our kind of database interaction abstraction for reactive relational database interaction. It comes with several drivers of its own. So for Spring Data R2DBC, you may choose to use any R2DBC driver, like the one for Postgres. There are early access ones for quite a lot of databases out there already. All right. Basically what I've just been saying, there are 3 target transaction managers, R2DBC, MongoDB, Neo4j. There's common setup. So add-enable transaction management, as you always do, but keep in mind you need a dedicated implementation. A standard transaction manager is not going to cut it. Theoretically, you could even mix and match both styles of transaction management within the same application. That reactive endpoints or reactive interaction chains use reactive transaction manager decoration, and that other interactions, repository interactions within the same application use platform transaction manager. You can mix and match here. I would recommend architecting for a single interaction style with the data stores in any particular service, in any particular application. Just because you can mix and match doesn't mean you should be doing it. But there might be reasons why maybe some services are co-located in the same application context, and then you can mix and match if it makes sense for your purposes. Right. Another new or revised facility is reactive messaging, where our good old message mapping annotation that we've been using for a stomp on WebSockets, for example, where incoming messages are being passed into the method and a kind of response message goes out, a reply message is being returned from it. This model existed for quite a while already, and it's now been spiced up with reactive support. If a message mapping annotation, a messaging endpoint here, has a reactive return type, or even a reactive type coming in this case, just like WebFlux methods, like reactive web endpoints, then we know what to do with them. We now automatically adapt them to our reactive messaging architecture. So we know that the reactive streams publisher has to be registered in the corresponding way with the target messaging system. Or if you even want the incoming payloads as a reactive streams publisher through declaring a reactive flux here, you want an incoming stream of elements, then we try to adapt the target messaging architecture to this reactive streams endpoint method automatically. This is primarily designed for RSocket, so it connects immediately to the RSocket topic, where a RSocket itself, as a messaging architecture, as a messaging abstraction, is reactive streams based. It's very straightforward to adapt methods like these, endpoint methods like these, to RSocket underneath the covers. That's what we primarily architect this for. So there's a whole class of applications emerging out of this that we expect to become a kind of dedicated kind of setup. RSocket-based applications that don't have any other endpoints, their whole purpose is to interact with RSocket channels. This also shows up, of course, in Spring Boot 2.2. The core interaction facilities, the core endpoint mechanism lives in Spring Framework 5.2, as indicated here. If you're interested in RSocket, we have plenty of resources out there, also on YouTube and on the blog. It's quite an interesting reference case for what can be done with reactive streams publishers in a messaging architecture with stream level back pressure. But I find it almost more important that RSocket comes with other qualities, like the session resumption. It's very much designed for scenarios where like mobile clients over less than stable connections have long-running interactions with server-side services. It's in particular designed for those kinds of target scenarios and has plenty of support from major players in this industry already. All right, so much for reactive messaging. Another facility, not the last we're ever going to touch, but the last that we had on the 5.2 roadmap, is reactive application events. At event listener methods traditionally are being called from a standard form of multicaster. It had some basic async support, but the standard multicaster basically runs the event listeners within the caller's thread. So there's it's events for decoupling, not events for async execution. That's what you would typically have used event listeners for. Now we are revisiting this from a reactive perspective. asking the same kind of question, basically. What if an event listener method returns a reactive type? What could this mean? What is this supposed to mean? It clearly doesn't mean that we'll just throw away the return type as an event listener method would do. Because there is no, that we publish a response that contains this mono. It doesn't make any sense. We really need to handle this specifically. So we know that those are reactive types. We know that a completable future is kind of an async type, and we take them as what they are. We subscribe to them in the background. We run them on the reactor scheduler, and allow you to compose an event-based architecture where certain event listeners might want to run immediately, like in the callers thread, and others might individually choose to run on the reactor scheduler in the background. So this is also a very fine-grained use of reactive programming. You may choose to use it for certain event listeners only, or in a completely reactive architecture, you might, of course, design all your event listeners or along the same style if you choose to do so. This is a general line of evolution that we see here, fine-grained use of reactive facilities all across the framework. There are further areas that we haven't covered in 5.2 yet. For example, add-scheduled methods. We'd really love to have some first-class reactive support for add-scheduled methods, but that's a 5.3 topic. Now, I've been referring to reactive API types. As the kind of to wrap up this section, let's quickly define what we actually mean. It's usually reactive streams publishers. It can also be, it can be direct implementations like in Reactor, Reactive Flux, Reactor Mono. There's first-class support for those two types in particular. We also support the RxJava types, flowable in RxJava 2 or the good old RxJava 1 observable. We support Java util concurrent flow publisher implementations. That's JDK 9's version of reactive streams. And we also consider completable future as a sort of reactive type. Wherever we support reactive streams publishers, we usually also try to support completable future if it makes any sense. For basically simple async handoffs that don't need full reactive streams support. And last but not least here, our Kotlin coroutine support, not the main topic here today, but shown in the keynote this morning. The Kotlin coroutine support works with the same facility. It's effectively reactive API adaptation because Kotlin coroutines come with a rich runtime API infrastructure underneath the language feature based on a Kotlin flow type, not to be confused with the JDK 9 flow type, different thing. A Kotlin flow type and a Kotlin deferred type that is being used as a return value underneath the covers for a suspending function. And from a framework perspective or from any kind of integration perspective, that's what we interact with when you choose to use Kotlin coroutines at the language level. What we internally do is we take a Kotlin flow and adapt it through our reactive API facilities to reactive streams, to reactor flow, to reactor flux underneath the covers. A very straightforward adaptation. So kudos to the JetBrains team working on Kotlin here. This is really a fine design. It's reactive streams compatible out of the box, can be very straightforwardly adapted to a reactive streams-based stack as we have it here. This also empowers us to bring further Kotlin coroutine support to you in 5.3. We'd like to extend Kotlin coroutine support beyond WebFlux, which is what it is primarily aiming for now, to also provide Kotlin coroutine support, for example, for Spring MVC reactive endpoints, Kotlin coroutine support for reactive transactions, Kotlin coroutine support for init methods. On startup, there's quite a few cases that we identified where the use of Kotlin coroutines would benefit from a specific integration with the framework underneath the covers. And it all goes down to the same facilities. So there's no parallel world here. Kotlin coroutines are just a language feature adapted very straightforwardly to the common reactive stack. Right, this is everything I had for you today. Quite a personal selection of highlights and kind of work items with a lot of merit, even if it might not be immediately obvious. All of those things are going to hopefully have some benefits for you. So I hope there's I hope that there's a lot of goodness underneath those covers showing up and revealing itself to you, if not right now, then very soon from now, through everything we're doing here. And everything we talked about basically ships in 5.2, just a couple of, days, a week ago, roughly. As I indicated, a lot of it is going to continue in 5.3. So many of the work streams are immediately continuing in 5.3, kind of further RSocket support, further Kotlin coroutine support, completing those storylines, further Reactive Transaction Manager implementations. I could easily imagine those sorts of efforts. And further performance tuning facilities along identified scenarios that we're trying to optimize. GraalVM support, GraalVM native image integration it's hopefully going to be a key part of that performance story in the 5.3 timeframe. Don't forget, Spring Boot 2.2 is coming soon, so you're already able to consume all of this through start.spring.io and using Spring Boot 2.2 release candidate 1. It's going to go generally available soon. So all of this goodness, also the combination of the Spring Framework 5.2 features and the Spring Data More, R2DBC, Neo4j, MongoDB features, the entire package combined is going to be available through Spring Boot 2.2 for you. Well, so much for this storyline. I am perfectly happy to take questions. We can take them in the auditorium, or we can have individual conversations afterwards, as you see fit. Sure. So are the slides going to be available? Yes, they will be for all of the talks here. And there's also going to be a recording for it, so you'll be able to catch up with it. All right. Any other quick question for the auditorium? Otherwise, please just come up to the stage and catch me afterwards. I'm around all week, so catch me later on as well. Thank you. Thanks for your attention.